you're like, Thanksgiving is a full week holiday. You
I
might have a lot
don't
of
know
things
what's
to do.
wrong.
Yeah.
This is how we do it.
Yeah. So we'll do that. Then we'll have one more week. Well, there's 2 weeks of lectures after that, but we just have one more week because like the last week of lectures is a networking projects week. So we'll do 1 week there, and I have not decided exactly what to do that week. So that's gonna be up for grabs. Maybe we'll do a poll on Canvas, like to people can vote on some of the ideas that were up here, or I might just do something that I could possibly lecture on because we're coming to the end of like the things I know about deep learning. Sound good? Right. There's our map that we did here. All right. So we'll launch right into metric learning. Hopefully that comes up. All right. Okay, metric learning. So we did generative models, and like a way of thinking about generative models is learning about like low manifold descriptions of low-dimensional manifold descriptions of things like images. So something related to this is what's known as metric learning, and you're like looking at all these pictures of Brad Pitt, wondering what in the world does this have to do with anything? So, so anybody recognize every single one of these Brad Pitts? Anybody like a huge Brad Pitt fan out there and like watching all the movies and stuff? Yeah, good. All right. So I recognize some of them. Like this Benjamin, what's it called? The Curious Case of Benjamin. It's like that's a great movie. Anyways, and there's oceans like one of the oceans 11, 12, 13. And those are awesome movies. But some of these I'm like I don't know. Like the shirtless ones in particular, I have no idea.
You got Fight Club.
Yeah, Fight Club, right? What was that? Yeah, River runs through it. Yeah.
Enjoy.
Cool. Yeah. See, there are some closet Brad Pitt fans out there. All right. So, what's this got to do with anything? Well, so when we've been thinking about classification, we've talked about like 2 different kinds of loss functions, but really only focused on one, softmax, right? And there's as many. This is basically a vector of probabilities for all the classes. So like, what happens when the number of classes is really, really, really big? I don't know, like hundreds of thousands, millions, the number of people on the planet. What happens in that case? Like, you can still use a softmax, but you're going to have, for one thing, you're going to have a ton of weights going from like, the end of your network to the softmax layer. There's just like, n times m number of weights there, and that could be a problem. That could just like be way too many weights. And what happens if like you are continually adding data to a model, and like the number of classes could change? So for instance, I have this up here because there's this cool problem that's like basically solved in all of your photo applications that are like, these are like, give me all the photos that contain this person, right? So this is like the Brad Pitt photo album. I love Brad Pitt, so I take all the pictures of him while I'm watching the movie, and then in my photo app, it's like recognizes Brad Pitt all over the place. Like, how is that happening? Because like technically there could be like this works on Facebook like really well, scarily well, where people are tagged, and once they're tagged, they start learning like what they look like. And there's billions of users of Facebook, and so if literally they had like some images for every single one of these people, and they want to be able to distinguish them all, like you'd have a softmax layer with like billions of labels. That seems crazy, right? So like, how does this work? How do you do this? And one approach that works really well is called metric learning. So, by the way, this is cartoon. So is that. So is that. So some of these, and that's a shrimp over there. So, this should work in all cases, but yeah. So the question is, what do you do when you have too many labels, or like if that set of labels is changing? Like, let's say that your training data is accumulating over time, but it's going to like in the case of faces, like every once in a while, like a new face shows up that a new person shows up in your database of faces, and yeah, what do you do? What could you do in that case? So a thing you can do is, instead of learning to classify to that label, you can learn to take all the things that have the same label and push those together in some representation space, like on this manifold. And if things are different, you can learn to push them, like from a different class. You can push them apart. So this is different from saying, like, I'm from this class. What you do in this case is you take pairs of examples from either the same class of things or from different classes of things, and you either pull them, or you push them together if they're from the same class, or you pull, or you push them apart. So, a pretty straightforward way of doing this is what are called Siamese networks. And that's maybe a slightly insensitive term. I apologize, but this is what they're called. Siamese networks. And so the way it works is that you basically have, like in this case for images, where you're trying to say, these are both Brad Pitt. You're not going to explicitly train it to say, like, this image predict that it's Brad Pitt. What we're doing instead is we're taking all the examples of Brad Pitt in our database, and we're running them through a CNN, a convolutional neural network, that share the same weights. This picture right here, this thing right here, is to say these are the same networks. They're exactly the same networks. You're gonna learn the weights for them at the same time, but these are two different networks. They're exactly the same network. They're learning to embed these similar kinds of images. And then what happens is, so they get embedded, right? So there's like some function here, D, and they get embedded. So like they're like some vector representations. You're not getting to like the fully connected layer in a compositional network. And then what you do is you say, okay, you pick some metric of similarity, some distance function. In this case, you have like an L2 distance, but you could pick like cosine similarity or whatever you want. And then you minimize that. You say, like, when these two are the same, push these things together. Or when they're different, push them apart. So what's on this board here is this idea. So for an example, you could have your distance metric be something like L2, but it could be any number of metrics. This is the metric part of metric learning. And then your loss function just depends on whether these are images or data points from the same class or images from different ones. So you could imagine there being some other picture here that wasn't a Brad Pitt, and you'd want to make sure that these weren't pushed together; they were kind of pulled apart. So in this example, like there's a delta parameter here that just indicates if delta is equal to 1, then these are two from the same class. If delta is equal to 0, then so like you get this part of the loss function. If it's equal to 0, you get this part of the loss function. And so when they're from the same class, then you get this thing here, and you just want to push them together. But when they're, say, from a different class, you pick up your old buddy hinge loss, and you want to push them away from each other by some margin m. Remember hinge loss? Seems like a long time, doesn't it? Hey there, hinge loss. Good to see you again. So that's it. So you push similar things together, and you pull different things apart from each other. And yeah, this can work. However, there is a kind of like failure mode for this, and what can happen is that you can in that network, you always have a pair of things, and they're either like from the same class or from different classes. So like each instance of the loss is just focusing on like either pushing things together or pulling them apart. And that can actually have like a failure mode, like basically you can learn to map everything to say some constant. It won't do that exactly because of the margin loss, but like if you have far more examples like one class and another, like because these things are being optimized at the same time, you can get something like basically this thing is learning to just map to a constant. So how to prevent that? Well, there's like lots of ways to prevent that, but a really common way to do this is what's called triplet network. So Sounds like kind of like a Siamese network, but this time there's going to be 3 things involved. And instead of doing the pushing and the pulling at different parts of the loss function, you basically just do it all at one time. So, so it looks kind of like this, where your objective function that you are optimizing for is going to work in the following way. So I should have mentioned when we're in the Siamese network. When you're training that, when you're generating the batch, your batches have to have, they're organized in pairs, right? So you have pairs of stuff that are either, from the same class or from different classes. Here, you have triplets of things. And the way it works is that you have what's typically called the anchor data point, the anchor example, and then you have 2 other ones. One is another example from the same class, and you have another one from a different class. So of course, I'm just going to joke you have to be there because they're as different as can be these days. And what happens is now instead of having just just embedding these these things in pairs, again you have a convolutional network, but the weights are shared across all these. So basically, you have exactly the same network across all of these things, or network for each one of these images to embed them. And then what you do is for that triplet, it's hard to see up here, but there's an anchor, there's an A, there's a positive example, P, negative example. So what you're trying to do is you are trying to have the distance between the negative example and the anchor. So this is like the pair that's different. You want it to be greater than the distance between the anchor and the positive example by, again, some margin. Here it's alpha, but again, there's some margin there. So instead of it being a separate, push these things together to 0 or a change loss for the other one, you sort of just do these at the same time. And then every single contribution to your loss function is a term like this, and you can formulate it like this right here. The idea here is like what you're seeing here. So your embeddings might start off in this way, where so this guy right here in the middle. This is your anchor. You have the other blue examples is another image from the positive class, or data point from the positive class. Your red is another data point from the negative class. And if they're situated like this, what this learning is trying to do is simultaneously bring in the positive example closer to the anchor and push away the negative example, again, by some margin, alpha or m or whatever. And that seems to work a lot better. That prevents this collapse, this kind of this behavior that you definitely don't want. So that your embedding space, your layer from a fully connected part of the network that represents these images is not costing to some point, but learning nice rich representations. And this is basically this is what's used in your photo applications to do this kind of recognition. You can pre-train it, of course, on lots and lots and lots of stuff. And then, as you start bringing your examples of faces, then you can adjust the weights in your network to learn about the distribution of the people in your photos. And it works pretty well. So a paper on this. So here's some examples of this. Something called FaceNet from 2015. But it pushes all these images together. And in this paper, they show some examples of false accept, false reject. So false accept is these things, these images, they come in pairs, and I guess they're kind of hard to see up here. But they come in pairs. These actually are the same person, but they're different people, but they were within the threshold to say that they're the same person. And then these ones over here are actually, let's see. Oh, sorry. What did I say? These are different. These are the same. So these are different people, but it was said that they were actually similar. And these are the same person, but they were said to be different. And when you the point of looking at these examples is you can kind of see when you look at the images, why it might have gotten fooled on this. But the important part is like there's a whole, and you know this from using your photo app. There's a whole lot of different ways like your face shows up in, or your friend's face or your family's face shows up in photos, and yet it can learn, you know, in similarities between these to say that like, yeah, these are all from the same face. Pretty awesome. And again, like a nice application of the power of convolutional networks. Any questions on that? The reason why this is related to like manifold learning is like you're learning a metric on the space. So like that's like more powerful than just a manifold. Manifold is like something you know, you just have some guarantees around continuity, but here you actually have guarantees of distance, which implies continuity on the space you're working in. So, anyways, that's why it's related. Okay. That's all I have on that. I just want to finish it up. Let's see. All right, so now we're going to start into the neural machine translation. Is there? Yeah. Okay, so this is like a really nice application of neural networks that you might use. I mean, you might not use this as much as like a photo app application, but you could use it, and it's amazingly powerful. So, yeah, there's a lot of people in this world, and there turns out that there's lots of languages. I haven't actually verified that there are 7,000 languages in the world, but apparently someone has decided that's the case. And you know, there's this graphic right here showing something like this is the number in millions of users on the internet using these languages. So English and Chinese, very representative here, and then like this goes on to Spanish, and then I can't read the rest of them from here. But lots of different languages, lots of different users of different languages, and there's this like desire to be able to say take text and in one language and be able to translate it faithfully and fluently to other languages. And we're going to try to use neural networks to do this. And I saw this tweet like 3 years ago, and I thought this was really funny. So it says, Ford candy always seems like the output of a slightly undertrained neural net. And it's got these examples like, dairy milk is not so bad, but like, kind of funny. Musk sticks, yeah, that sounds terrible. This one's great. Pineapple lumps. And frogs alive. I don't think these were translations from actual candy names from like a different language, but when we're using neural networks to do these things, we often will run into like we'll run into this like these kinds of cases where it's like we almost got it, but you could tell there's just like something not quite right. Like I'm not really sure what was intended by musk sticks. Like I don't think musk is like a thing that you want to use. Yeah. So like for example, so if you went to this website, you would see in French, you would see something that says, however, within the discipline of machine learning, developed specifically or specificity that of deep learning. So like that doesn't seem like quite the awesome translation. So like this is like the kind of thing that you see a lot of. So like maybe here's like another way that this could have come out. Nevertheless, within the discipline of machine learning, a specialization called deep learning has been developed. You know, like nevertheless on there is kind of weird. You know, you get like poor word choices a lot. Like you know, especially like words that are a little more rare. So like here, peculiarity is somehow translated as distinguishing feature. You know, like it's kind of right, but it's also not like doesn't seem to like capture the intention of what might have been said there. Often get bad sentences like deep learning deals with computational elements which allow a network of artificial neurons to learn a model of the human brain. Up there it says deep learning aims to find IT elements, allows a neural network to learn about the human brain model. I mean, like, this is the kind of stuff that we want to try to avoid. Like it's really good, but not quite there. Like the best translation of what was there in French might be something like this. However, in machine learning, a specialization called deep learning has emerged that can be recognized by its instinctive neurobiological influence. Deep learning is centered around networks of artificial neurons, which can learn models of human brains. But came out to be this sense up here. So we want to learn how to get really, really, really good at this. And lots of people are working on this. With not surprisingly, lots of people at Google, lots of papers on neural machine translation come out of Google, and some of the universities that are really involved in this. So, even now, like if you go use Google Translate, like it does pretty well, but there's like some obvious gaps. So the intention for this lecture and the next one is to like kind of talk about the like what machine translation is, like briefly mention what it has been, kind of show like about 4 years ago some of the results that were coming out that were really promising, and how that's developed since to like what the state-of-the-art neural machine translation systems are like. So the last couple of decades, up to like maybe 4 years ago, it was really dominated by what's called statistical machine translation, or SMT. Anybody have any experience doing any of this stuff, by the way? Because this is not something I know any of. Okay. So the important part to get out of this slide is that the way that the flavor of things that comes out of statistical machine translation is a lot of different pieces that are brought together to provide like a lot of candidate translations, and then you sort of score those and say like you take the top scored ones. So like in typical like natural language processing, you do things like n-gram extraction. You may have done n-gram extraction. Something like you take like n words in a row, and like you want to be able to represent those things, like the statistics of like n words, like what those are like, the alignment of words in your source and target text. So source being like the language you're translating from, the target being the language you're translating to. You have models for how to go from one to the other. And again, the important thing here is that like there's lots of different pieces, and there's lots of candidates being produced, and then you score these candidates. So that's fine, and this actually works fairly well. The best systems for this actually work fairly well in terms of like some measurements of translation, but it is a big unwieldy thing. It's hard to say at the end of the day that like a statistical machine translation system like understands how to translate or how to do translation. That's maybe the key thing here. But like researchers in this field not only want to produce like state-of-the-art translation systems, but like you want to be able to look at like this model trained end to end and say like this thing has really learned what it means to go from one language to the other. And it's hard to say like in a system with all these kind of moving parts and like sort of different pieces that are concentrating on different parts of language, and then pipelining them all together, saying that represents some algorithm. So some of like the early learning based systems worked something like the following. You take a sentence and then you would break it into chunks, which means like breaking up into a what's it called, a grammar tree. So that basically you get things like parts of speech labeled, and you get that for both the source and the translation, and then you try to say like for each one of these pieces what should it translate to, and then try to like align the pieces up accordingly, according to like the grammar of the particular language that you're translating to. So one of the important things about this is like the translation only happens locally in the sense of like each of these chunks is being translated independent of the other chunks. And that's like, you know, like that got some results, but it also doesn't feel like whatever's involved here, like whatever, you know, learning models or language models are involved here, like are actually learning anything, because it's just learning to do like simple things like dictionary lookups, so to speak, you know, like going, like, you know, learning to go from she loves to, and by the way, there's going to be a lot of like English to French here. This is like a typical task. Slightly more sophisticated is something like the following, where you learn like longer, you learn to translate like longer pieces, not just like parts of speech, but like longer parts of the sentence and relationships between those, and have like the translation be conditioned on like words already produced, like in this case. But again, the translation is still happening locally. You're only doing it like in chunks at a time. So really, you know, to do this right, like it feels like the thing that needs to happen is, you know, you want to be able to go from give me one sequence and translate that of words and translate that whole thing into the other language, that whole sequence that produces a grammatically correct, fluent translation of that. So like in this, you know, case, taking the sentence "I am a student" and giving that to a network and some model, and then what it gets back to you is not just like a local translation of pieces, try to like realign them, but to produce in French, "Je suis étudiant," which may or may not be proper French, but doesn't really matter yet. So the goal here is to do end-to-end translations from the full sequence to the full sequence. And the two papers, there actually a number of papers came out around this time, and a couple of ones like a little bit earlier that were sort of anticipating the pieces being used here. These two papers right here are the important ones. And so we're gonna see like we're gonna basically like these two things are like very similar approaches. We're gonna go through like a combination of the two approaches. So yeah. So the important part here is like what we're going to do is we're going to be using recurrent neural networks to be able to encode full sequences, and we're going to use this as like an encoder decoder. So we've learned about recurrent neural networks. We've learned about encoders and decoders. This is not an autoencoder, because we're not going from like "I am student" to "I am student." What we're going from is encoding "I am student" to some representation that gets decoded to the French "Je suis étudiant." So like there's this notion of encoding and decoding, and so it's just bringing together a couple of different things that we have learned. So we've just gone through a lot of this. This is just a brief recap. Remember what we're doing here is the basics here are just we're using a recurrent neural network to represent sequences. And they're going to be sequences of words. And of course, words are, there's a lot of words. Vocabularies can be quite large. Even in like restricted like corpuses of documents or text, like they can be quite large. So there's going to be a lot of words. And this actually is something when we look at the more advanced systems, there's going to be a move away from words to actually just doing character translations, so character-to-character translations to sort of combat this like huge. So like alphabets are much smaller than vocabularies, right? But all this stuff, you know, from just 2014, you know, only 4 years ago, these were using words. So the sequences are sequences of words, and you know, you've done your homework. You know a bunch about simple, plain vanilla RNNs and also LSTMs. So the way that this works in neural machine translation is the following. So there is there is a source sequence. I am a student. There is a target sequence. Anybody want to like correct that? By the way, like a French speaker. What's that? Yeah, exactly what she said. So the basic mechanics here are: you start at the beginning of your sequence, and you input the representation for that word, I, and you might have a couple different layers. In fact, one of the things that is in these papers that is impressed upon the reader is how important depth is in these numbers. I'm only showing 2 layers of depth here, but like in those papers, there's 4 layers of depth. And like 4 was really important. 2 didn't learn to do translation as well as like 4 layers of depth. So having layers of depth in your recurrent neural networks, so that you're learning like greater abstractions of the words and the sequences was really important. So of course this just this just keeps moving forward. So once you have that representation of that word, that gets passed on to the next cell in the recurrent network, and you have both input coming from the next word in the sequence, and you have the hidden state coming from whatever layer you're in being passed into there. And so this is how you keep track of like the state of the sequence. The state of the sequence is being captured in whatever's coming out of here, this hidden state, and you always have the input, the next word in the sequence. And yeah, do this, keep going, and then you get this whole thing. Now, what we haven't really done, I mean, we kind of alluded to it, we haven't really looked at is the fact that you can take these RNNs and you can stack them up together. And in this like encoder and decoder sort of way. So the way this works is the RNN that represents the source sequence, the source phrases. This whole thing's gonna be trained end to end from encoder to decoder, but its job is to produce some hidden state from here that's going to be used by the decoder to decode to this other language. And the way this works is the following. So the encoder encodes a state, and an important thing to get out of this is the fact that like the layers are preserved temporally. So like the hidden state coming out of this first layer is passed on to the first cell in this decoder RNN. Let's see. So how this works is, at least in these networks, is there are these additional words that are introduced into the vocabulary that indicate like the beginning of a sentence and also the end of the sentence. These boundary markers. So when you go to translate this sentence, the thing you feed in, like the word from the vocabulary that you feed in to the first input for this decoder network is this like start word. And then its job is to learn to produce the appropriate words in the translated sequence. So the first one being je, whenever wants to correct that, and then and then so forth. And then finally, there's another marker indicating the end of the sequence. And this just helps like the network to know, like when you actually want to translate this learns to take this input and then produce the output, but then eventually it will produce the end of the sequence. So like this is when you should stop. It's going to tell you when to stop. It's learned to say like this is the end.
Number of inputs and number of outputs, they don't have to be the same, right?
No, they don't have to be the same. That's right. Like they end up being the same here because of the boundary marker, but they don't have to be. That's one of the nice things about using this recurrent neural network is that you get this flexibility in doing that. So yeah, you can have like this is one of the important things about doing translation, right? Is that it's certainly, it's certainly not the case in general that you have the same number of words in your vocabulary in one sentence and in the translated sentence. So yeah. So like that's like the that's the crux of it. So a couple of things on this. So one is that you can't just like give this words, or so one way you might have thought about doing this is to say like, oh, I have 100,000 words in my vocabulary, so I'm going to use 100,000 one-hot vectors, so just like, it's a vector of length 100,000 that is, you just order all your words in some way to say, well, the first one will just have the vector that represents it is has a 1 in the first entry and zeros everywhere else, and the second word is a 1 in the second entry and zeros everywhere else. You could do that, but that would be like a really expensive, computationally and memory-wise way of like encoding this vocabulary. So one improvement in how to do this is to start with using word embeddings to go from like this sparse representation of these words, these one-hot vectors, and to embed that into to transform those into dense vectors in a much lower dimensional space. So this is like some pre-processing you might do. So like think about it as like a pre-trained model. So many of you might have heard of before of like word to vec. Think of this as like a really shallow neural network that just learns to linearly transform your one-hot encodings of these words into shorter, dense vectors. So if you do that, like this is really good for the network. It's compressing a lot of information. Word embeddings are really cool on their own. With certain of them, you get like nice like arithmetic properties, kind of like we saw with the images the other day, where you could like put glasses on a class in the generator. Like you get certain things like certain properties like that out of the arithmetic, the vector arithmetic there. But regardless, if you start with those for both your source language and for your target language, then this really speeds up training and makes it feasible. So like that's one trick. Also, in doing these, especially to handle like multiple length sequences of like all different kinds of length, it helps to have like initial hidden state that gets passed on these, and it's often just set to like the 0 vector. So just a bit of mechanics. And actually, as I'm talking about this, I realized I don't have this here, but one of those papers found it was really advantageous to turn the sequence of the order of the words in the translated sentence around. And they claim that was really important because like they got some like improvement in the results, and they say as well it's because like the LSTMs that are involved in learning this whole thing like have an easier time of learning the relationships between like this word and this word, which are more likely to be related just because of the position of the sentence than like say like this word and this word, and that helped out. But not all the papers do that, and I don't think any of the papers anymore do that. But that was found out to be like advantageous. But the way that like information flows in these kinds of networks is, you have your inputs flowing up into the network. You have your hidden states flowing temporally in the sequence, in the direction of the sequence, and it's important to note that like again I already mentioned this, but like the layers are preserved in this encoding and decoding. So like hidden states in the first layer of the encoder are passed on to hidden states in the first layer of the decoder. Same thing with second layer of the encoder being passed on to the second layer in the decoder. And You can, of course, throw in plain vanilla RNN, but you wouldn't do that because you all know that LCMs solve a certain problem like vanishing gradient problems and whatever. And once you have that, the way that this works for training is the following. So when you train this, there is a loss associated with each of the outputs from each of these like vertical parts of the decoder. So this is producing, this is taking the hidden state of the encoder and the start marker, the start word in the vocabulary, and the training data is we want to produce, in this case, je. So you literally are trying to maximize the likelihood that is the probability of that happening. Because again, what's happening here, at least in these models, is that there is a softmax basically at every single one of those outputs over the entire vocabulary. So where I just got done talking about metric learning and saying, what do you do when there's like hundreds of thousands of classes, that could be a prod off, then you just replace it with another token called unknown, and so this is how you sort of get over the fact that there's hundreds of thousands of classes here. So instead of having millions, you might actually have hundreds of thousands because there's lots of rare words. It's kind of weird and kind of like doesn't feel right, and the better translation systems have ways of getting around this, but there is this fact that at the output of every single one of these things, there is a very large softmax layer. Again, over the vocabulary. But regardless, you're going to have this for each one of the words in your training data, including for the end token. And once you have that, then you can use those losses to do backpropagation and train these things. So you start up in that upper right-hand corner with the loss for the last token in your sequence, the last word in your vocabulary or in your phrase, and that just backpropagates. So there's some loss associated with the probability that you assign to the correct class for that turn in the sequence, and so forth. And you can see as you go, you're backpropagating both backwards in time, but also I guess backwards through the layers of your both the decoder and the decoder. And yeah, and it's stochastic gradient descent all the way. So it gets trained end to end. So in this way, you are learning to translate this phrase into this one right here. Not breaking this up into chunks and just looking at different pieces, but actually taking the full input sequence and giving the full output sequence. Okay, questions on that so far? All right, so training versus testing in these kinds of systems. So yeah, when you're training like we just spent a lot of time with, the way this works is that somebody gives you training data that is, this phrase in the source language, it should translate to this phrase in the target language. So that's like the best way to train this. You can imagine where you might have like a book, in two different languages, and you might hope to use that book and just break up the sentences in each one of these things. And if the book's been translated faithfully, that might work. But you can also see how there might be a mismatch in the number of sentences or alignment of sentences, or I don't know. For two different languages where grammars are very different from each other, punctuations treated differently, that kind of stuff. This becomes a much harder problem. But for Latin languages, this is really easily. For English is something else. That's Latin based or Germanic or something like that. This is fairly easy to do. But you do need to have some. You need to have something already where you have these pairs of source and target translations. Now, when you're testing, of course, you are you're only given the source. Well, you also when you're testing, you also have the target, but you're not supervising it, right? So like here, it's pretty clear how to supervise it. But what do you do in the case where you have the input settings, but you don't you need to produce the output? And the way that works is probably as you're imagining it should work is you give the encoder network the phrase that will produce a hidden state that will go into the corresponding layers of the decoder again, like this is like the representation of this whole phrase coming into the decoder, and then you're given the start token, and then you're going to get an output that is going to be a softmax output. So it's going to be a distribution over your vocabulary. Of course, in this case, it's a very limited vocabulary, but the idea is you look through this and you say, okay, whichever term, whichever word was given the highest probability, that's what we're going to put here. And this is showing that this isn't quite translated exactly the way it was trained to translate. Moi got the highest probability for some reason. But whatever it is, it's the most likely word, and then that becomes the input for the next step in the decoding. Right. So if that's incorrect, you're going to start to accumulate some incorrectness, right? It's not totally devastating because this hidden state now that's coming into the second stage of the decoder is a combination of the hidden state from the encoding, but also the hidden state, but it's been adapted slightly to so that so the state knows that this is the second term to be produced. So, anyways, there's still it's still going to be conditioned on what's coming out of here, but as the sequence gets longer and longer and longer, the influence coming from the encoder state will diminish because you're building up so much state in the current translated phrase. But you just follow this procedure. So now that you've got this word here, this goes as input, you have your hidden states, that produces now another output, softmax output, so the distribution of your vocabulary. You pick the most likely word, and you keep going, and eventually you're going to produce the stop token, and then you stop. And you cross your fingers and say, hope this is it. Hope this is right. This is not too bad, but it's grammatically incorrect, I guess. Me am the student, or whatever. So, yeah. This is made up. So, just illustrative of what could happen. So, one of the big questions here is how do you decide? Oh, sorry, one more slide here. So, this kind of procedure for generating this sequence falls into the class of algorithms known as beam search, which is basically just to you're at a certain state of some sequence. You look at all the possibilities. You choose. You have some heuristic for choosing the next one. In this case, the most likely next state, and then you move to it. And then now that you're there, you built up some history from where you were, and then in that new state, you do the same thing and look at the most likely. So anyways, this is just a very simple beam search decoder. So not terribly sophisticated in this sense, but it seems to work. Okay, so how do you evaluate how well you're doing on these things? The main accepted way of doing this is what's known as the BLEU score. BLEU. And this is bilingual Oh shoot. Somebody look it up real quick. Is it something about like translation between two languages? Why are you behind? Totally blanking. Bilingual evaluation and understanding. Thank you. What it is the following. So let's go back here actually. The correct translation here would have been je suis étudiant. So it's pretty close. It's only off by one word here. So the way that the blue score works is to look at your candidate translation, look at the actual one, or there actually might be a number of ones that would be accepted, and you compare against all of them and then average this. But you take a candidate, you take your candidate translation and then like a correct one, and you just see how many words match up between them, and then you divide by the total number of words, and that's a score between 0 and 1. And then, like, if you were paying good attention, you'll see that this is not a score between 0 and 1. So this is that score multiplied by 100. So like this is just to like account for the fact that you might have very long phrases, and I don't know, you multiply by 100, you might be a little bit easier to think about these than just looking at 0.33 or 0.27. I don't know. It's multiplied by 100. So that's how it's done. And then again, like there might be a number of like correct translations, and so you would compare against all of them, and then you take the average blue score of all of those. That would be like the blue score for that particular translation, and yeah. So this is like the average. So these numbers you're going to see here are the averages over all of them. So this English to French WMT 2014 is a corpus of English to French translations. So the state-of-the-art SMT, so the Statistical Machine Translation System, in 2014 was something that would get a blue score of 37. So if you think about it, that's something like 37% of the words are shared basically between the two translations on average. It doesn't seem like amazing, but this is like 2014 total state of the art. And then the average statistical machine translation system, got something about like 33.3. So how do these two, how does this approach the RNN encoder decoder? Oh, by the way, this RNN encoder decoder has a much shorter name. It's called seq to seq, sequence to sequence. So SEQ2, because like, yeah, that's cool. SEQ. So seq to seq. So like that technique that we just went through is called seq to seq. And why I don't have it named anywhere, I don't know. But seq to seq. So how does seq to seq work on this? Well, this seq to seq system, one we just looked at, this is actually the one that takes the target sequence and change it, reverses the order. It got a blue score of 34.8. So that's comparable to the average. It's a bit better than the average, and about comparable to the state of the art. Although it's really like unclear, like what 2 percentage points here mean. For me, it's unclear. But then they have this interesting score, which was, remember that the statistical machine learning translation produces a bunch of candidates, right? So what this did was it took all the candidates and used so it took all the candidates coming out of this system, used the neural machine translation to basically like rescore them, take of all the candidates that were there, take the one that was most likely under the neural machine translation loss function, so the one that's most likely, and then have that be the translation. You can see that it did almost as well as the state of the art SMT. And the point that's being attempted to be made here, anyways, is this took many decades, 2 decades, many years to do this sort of manual extraction features of language and put all the pipeline stuff together. This was an end-to-end training, 1 to 2 years of research, on the types of RNNs that might work on this, and then getting nearly state-of-the-art results. So that's again we saw something kind of similar to this when we were looking at convolutional networks and how they sort of blew the manual extraction of features. So the systems are built on manual extraction of features from images. This is something kind of akin to that. And there's been a lot of improvements that we're going to go over the next time we meet that that get us far above this state-of-the-art 37 score here. Let's see. Yeah. So this shouldn't say mine. This should say this should say the seek-to-seek right here. So what you're seeing here is around this time there were a number of different neural network approaches to this. When we showed here, we had the best results. This is a deep LSTM. So again, I've already mentioned this, but so it was 4 layers. So that might not seem deep when we talked about 50 or 100 or 1,000 layers in a residual network. But that's pretty deep for these models, especially if you think about the dimensionality of the outputs and the hidden states that are involved here. Anyways, 4 layers, and yeah, nearly state-of-the-art results. There were some other types of recurrent neural networks used, getting decent results. And there was also this attempt to use convolutional networks to sort of represent, embed the phrase, the phrases, or encode them, but not all that amazing results there. But just noting that was there. So what could possibly go wrong? We have this awesome system for doing machine translation. What could possibly go wrong, right? Well, to be honest with you, I don't know for sure if this was actually done by machine translation, but these are just really funny pictures of machine translation. This one's great right here, deep fried baby. Anybody speak or read any of these languages that are up here that can confirm, or that could tell us what you think the correct translation might have been? So I really don't know what this was supposed to be.
It's like sale of chicken.
What's that?
Just like sale of chicken.
Yeah, maybe. Sale of chicken, sale of dead chickens. I don't know, might be a particular language that might be appropriate to say the chicken's dead, or the chicken's we're not selling you a live chicken, we're selling you a dead chicken. But this somehow got translated as sale of chicken murder. This one's really awesome. So it's telling you where the restrooms are. Go back towards your behind. Yeah. I honestly, deep fried baby. It was baby walk, baby noodle. So maybe it's a deep fried baby noodle. But somehow the noodle part didn't come out of here. Deep fried baby. This one has no explanation. Meat mussels, stupid bean sprouts. So the point here is that translation is actually really, really, really hard because there's so much. It's not just so these systems are awesome because they do end-to-end training. So you give it a long sentence or phrase, and you translate to a long sentence or phrase, and that does encode some of the context of what's going on in the sentence, but not really. Don't in these kinds of examples that are mostly advertisements. I mean, there's a lot of assumed context there that you just don't have access to in the even the translation, right? So it's not surprising that you don't that this doesn't come out to be something more sale of dead chicken. I don't know. It actually not surprising. What you can imagine is when the system this was trained on, when it saw dead, it whatever the word was for dead in the source language, that was often associated with murder. I mean, it's just whatever the corpus was, right? So these systems can't be blamed. They're only as good as their training data, So, like, what are some of the limitations that are causing this? So, I already mentioned this before a number of times, but one is like just the vocabulary size itself. Like, language is particularly hard because there's all these discrete tokens that carry meaning, and the way that they go together, like the order they go together, creates like additional meaning. And so like the vocabularies are already very large, typically hundreds of thousands, maybe millions of words that you might expect to see in a corpus. But beyond that, like the order in which they come also matters, right? So like this is hard. So so to get better at this problem, like we might hope to extend our ability to like cover the vocabulary, cover like the meanings of different arrangements of vocabulary. Another problem in this is just sentence length. So this is a recurring, I guess pun intended, a recurring problem of recurrent neural networks, where like there's a means for encoding the state of the sequence, but as this gets longer and longer and longer, it just becomes harder and harder and harder to maintain like all the important parts of the state of that phrase or that long sentence, in a vector of finite size. It's just like information theory. It just becomes harder and harder to do. So if we could get better at like translating long sentences, then we might expect to do better. And then, just language complexity itself. So, like as we go from like one grammar to another, there's a lot of change in like the way that word order, first just like going from word to word, like what that, just finding like a correct word-to-word translation, or like a sequence or a small number of words to a small number of words to like maintain meaning. And then, just like all the complexities of language, all the complexities of grammar, all the complexities around like producing meaning in these arrangements of finite tokens is like, is super hard. So like being able to like handle more complex grammars might also be something that if we can learn, if we can make some progress there, we might be able to do translation a bit better. So actually, this is my last slide for the day. When we start on Thursday, we'll go through basically what has been done in each of these to try to address these problems and like the improvements that is given in the blue score. And yeah, so sorry, you got 10 minutes back of your day. I'm sure you wanted. I apologize. I cheated you of those. But yeah, happy to answer any questions. Other than that, here we go. Don't forget to vote. If you haven't done it already, and you're eligible. Those polling locations will allow you to register even if you're not registered. Hey, quick question about my
last two cells. It's fine, but then it's like I'm going to run them all together. Getting some variation.
So, and you put here is like so the output is like
Yeah.
So was my comment like, you're right on thinking, in your mind, you know what you're doing, that's what you're doing. You're not just reading words. I'm not
What route?
And yeah, so
You mentioned like the same day. That's just like the opposite.
So probably pretty straightforward. So you can explore things like, yeah, it's like totally intensive carousel. And you can see what the difference is. I wouldn't spend too much time playing around with like real architecture things like connection. Obviously, these are change number of units in time. So, another thing is there's some system for